Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you here with us today. Get ready, because we are stepping right into the dojo of practical physics. Today, we're focusing on the mastery of motion, forces, and energy. And we're going to do that by looking at 7 fundamental physical experiments, straight out of the Cambridge IGCSE Physics 0625 syllabus. But, try to think of these experiments not just as tedious schoolwork. Instead, imagine them as martial arts forms, really structured, disciplined ways to observe and measure the physical world around us. By the time we wrap up this session, you're going to have a crystal clear framework exactly how we extract truth from motion and matter.
Okay, let's lay out the trials of mastery we're going to undergo today. Trial 1 covers time and motion. Trial 2 explores the weight of matter. Trial 3 is all about the balance of forces. And Trial 4 wraps the whole shebang up with grounding and pressure. Let's just jump right into the first trial, shall we?
Trial 1, the flow of time and motion, mastering the basic quantities. Now, what's really interesting about this slide is how the simple pendulum experiment is broken down into incredibly clear variables. In any physical trial, you absolutely must know what you're changing, what you're keeping exactly the same, and what you're actually measuring. So, if we're testing how the length of the string, or maybe the mass of the bob, affects the swing, those are our independent variables. We have to control the amplitude, meaning we release the pendulum from the exact same angle every single time. But look really closely at that dependent variable. We don't just measure one swing. We measure the time for 10 oscillations. Why on earth would we do that? Well, because the time for a single oscillation is just way too short for human reflexes to catch accurately with a stopwatch. By timing 10 swings and then dividing that number by 10, we find the mean value, which massively reduces the effect of random human errors. It's a remarkably simple but literally a brilliant scientific technique. And that brings us to a really fundamental definition, the period. This is quite literally just the exact time needed for one complete oscillation of a pendulum, so swinging from its starting point all the way across and all the way back. Once you capture this single, highly accurate number, you actually hold the key to a much larger cosmic constant. In fact, if you want to go a little further, you can use the period of a simple pendulum to calculate g, which is the acceleration of free fall due to Earth's gravity. You just use the formula 4 pi squared L over t squared. Think about that for a second. Just by swinging a little weight on a string, you can actually measure the invisible pull of the entire Earth. All right, moving from the steady rhythm of a pendulum to objects actually in motion, we use a really cool tool called a ticker tape timer. This brilliant little device punches a dot onto a moving strip of paper tape exactly every 1/50th of a second. So, if an object is moving at a constant speed, the distance between those dots, or ticks, stays exactly the same. But if the object is accelerating, say it's a trolley rolling down a sloping runway, the distance between the consecutive ticks stretches out. It gets wider and wider. This brilliantly illustrates how visual tape charts can instantly reveal changes in velocity. It's honestly like freezing time so you can actually see speed. Moving on to trial 2, the weight of matter. This is all about measuring density.
Density is formally defined as the mass per unit volume of a substance, and the core equation for this is so elegant. Rho equals mass divided by volume. It's a real game changer, because if an object has a lower density than water, it floats. Higher density, it sinks. To figure this out, we simply need to measure 2 things: how heavy the object is and how much physical space it takes up. For regularly shaped objects, like a neat little wooden block or a metal cylinder, you just measure the dimensions with a ruler and calculate the volume. Easy, right? But what happens when the shape is completely irregular, like a jagged rock or some weirdly shaped piece of scrap metal?
Well, for those irregular shapes, we use a special technique called the displacement method. First, you pour some water into a measuring cylinder and record that initial volume. Next, you measure the mass of your irregular object on a balance. Then you just completely submerge the object into the water. Naturally, the water level rises, right? Because the solid displaces the exact same volume of water as its own volume. You record this new, higher volume, and the difference between your 2 readings gives you the precise volume of your object. Oh, and a quick pro tip for the dojo here: always make sure your eye is perfectly level with the bottom of the curved water surface. That's called the meniscus when you're reading the cylinder. That ensures your measuring technique is absolutely flawless. Which naturally brings up a pretty vital question when evaluating our experiments: how do we actually improve the precision of these measurements? Because it's not just about going through the motions, it's about the discipline of the observer. Improving precision means choosing instruments with higher resolution. It means avoiding those sneaky parallax errors by keeping your line of sight perfectly perpendicular to the ruler or the cylinder, and it means rigorously recording your final density values to the correct number of significant figures.
Honestly, that attention to precision is the true hallmark of a physics master.
Let's move to trial 3 and see how this builds into our next challenge, the balance of forces, where we explore equilibrium.
Now, this data table beautifully captures the essence of Robert Hooke's law, a concept from over 300 years ago. Basically, when you hang masses from a spring, it stretches, and provided you don't stretch it so far that you permanently deform it, that extension is directly proportional to the stretching force. Notice that last column, though. Extension is calculated as the new scale reading minus the initial unweighted length of the spring, which we call L0. I highly advise doing it this way. By reading the absolute position on the ruler first and subtracting later, you completely avoid those nasty little subtraction errors creeping up during the experiment. The relationship between the force and this extension gives us what's called the spring constant, which tells us exactly how stiff a material actually is.
Now, forces don't just stretch things, do they? They also turn things. And this introduces us to the principle of moments. The moment of a force is essentially just a measure of its turning effect. It's calculated by taking the force and multiplying it by the perpendicular distance from the pivot point. For an object to be in perfect balance, what we call in physics equilibrium, the sum of the anti-clockwise moments absolutely must equal the sum of the clockwise moments. To actually test this in the lab, we do this cool balancing act where we hang masses on a ruler that's balanced on a pivot. But remember, the equation calls for force, not mass. So that's exactly where this specific number comes into play, 10 newtons per kilogram. This is the gravitational field strength, and we use it to convert our physical mass into weight, which is a downward force. So to put that into perspective, a 10-gram mass doesn't exert a force of 10. You have to divide by 1,000 to get kilograms, then multiply by 10, which results in a turning force of exactly 0.1 newtons. But achieving that perfect Zen-like equilibrium requires a few really careful precautions. Before you even begin hanging things, you absolutely must balance the empty ruler itself. Sometimes you even need a tiny bit of blue tack if the ruler is slightly uneven. Next, ensure the ruler swings completely freely on its pivot, without any friction dragging it down. When you do start hanging masses, use string loops or rubber bands so they can slide smoothly to the exact right distance. And this is crucial. Support the ruler horizontally with your hand while you're attaching the mass. If you don't, the sudden weight might cause your whole apparatus to crash to the floor. Only when you gently let go do you see if the resultant moment is truly zero. Finally, we arrive at trial 4, grounding and pressure. This is all about investigating weight and area.
So, the crucial point here is understanding how gravity acts on objects. Every object behaves as if its entire mass were concentrated at one single point, and we call that its center of gravity. But how do you find it for a weirdly shaped, flat piece of cardboard and a regular lamina? We use something called the plumb line method. First, you suspend the shape completely freely from a pinhole. Gravity naturally pulls the object so its center is perfectly below that pin. Then you hang a weighted string, a plumb line, from that same pin and carefully trace its vertical path down the cardboard. Next, you hang the shape from a completely different hole and trace the new vertical path. Where those lines intersect, X marks the spot. That precise intersection is exactly where the whole weight of the object can be considered to act.
Of course, it's a whole lot simpler for symmetrical objects. If an object is regularly shaped and has uniform density throughout, its center of gravity is perfectly balanced right in the geometric middle. The exact center of a rectangle, the absolute middle of a circle, the dead center of an equilateral triangle. If you place your finger right at that geometric point, the shape will perfectly balance every single time. Now, take that downward force, like your own weight, and think about how it interacts with the ground. That is what pressure is. Pressure is defined as force per unit area. Imagine calculating your own body's pressure on the floor right now. You'd step on a scale to find your mass, convert it to a force using our handy 10 newtons per kilogram rule, and then literally trace your foot on a piece of graph paper. By counting the tiny 1 centimeter squares inside your foot's outline, you can calculate your total surface area that's in contact with the ground. And here is the really beautiful reality of the pressure equation. If you stand on just 1 foot, your entire weight is completely concentrated on a much smaller contact area, resulting in far greater pressure on the ground. But if you stand on 2 feet, well, you haven't changed your weight at all, but you have doubled the contact area. Because area is on the bottom of the equation, doubling the area exactly halves the pressure. Oh, and a quick tip when you're doing this experiment and counting those graph paper squares, to get a truly accurate area, only count the squares that are half or more covered by your foot outline. Well, we've covered a lot today: time, motion, density, balance, and pressure. But before we wrap up, I want to leave you with a fascinating question to really ponder. A mercury barometer measures the immense atmospheric pressure of our entire planet by balancing it against a vertical column of liquid mercury. Think about everything we've discussed today about density, force, and area. If you took that barometer tube and tilted it sideways, or maybe if you swapped it out for a much narrower tube, would the actual reading of the atmospheric pressure change? Does the shape of the container somehow change the vertical pressure of the liquid inside? I'll let you chew on that one. Thank you so much for joining me in the dojo of practical physics today. Keep questioning, keep observing, and I'll catch you on the next explainer.